All right. Well, I am really pleased to introduce Maurice GLEASON. He's here from the UK, and he does a lot of shows for us overseas. He's got a lot of great stuff up on YouTube, so if at any point you are looking for some kind of material to use to educate yourself or educate your project members, if you go to YouTube and you search for Maurice GLEASON DNA, you'll come up with lots of really good stuff. And I hope you enjoy extending the haplotree into a surname group.
Thank you very much, Janine. Good afternoon, everybody. It's great to be here. It's great to see so many familiar faces, so many unfamiliar faces. It's great to be back in Houston, and a big thank you to Max and Bennett and the whole Family Tree DNA team for organizing the conference and for inviting me to speak today. And I'm going to talk to you about how to build a mutation history tree. And this, in effect, is extending the haplotree into your surname project and into specific genetic groups within your project. Now, I'm going to try and finish a little bit early, but because I'm Irish, I tend to talk a lot. But it would be nice to have a little bit of time just to answer questions and have a little bit of a discussion. This talk is being recorded, I should say, and it is going to appear on my YouTube channel, which is simply DNA and Family Tree Research. And if you want to take any photographs of anything during the presentation, then please feel free to do so. So the whole idea behind this is that with a lot of us, our family trees end at a particular point in time where the ancestor run out. And the idea would be that after the ancestors run out, these human beings in blue, the DNA markers could possibly take over and go back in time, possibly even to the origin of the surname itself. So it really is a method of combining SNPs and STR markers with known genealogies, using DNA markers when the people run out. Because most of us, like I say, have this brick wall, and especially if you're doing Irish or English research, well, Irish research will end around about 1800. With English research, you can get back maybe into the 1600s, maybe into the 1500s. With American research, if you've got colonial American ancestry, you can get back into the 1600s pretty well. But even if you get back to 1600, and the surname has been around for 1,000 years, you're still missing 60% of your family tree is not going to have any ancestors on it, going back to the origin of that surname. So this is where the DNA markers hopefully can fill that gap. Is it possible? And I did talk about this 2 years ago here, and I have that video on my YouTube channel talking about combining SNPs, STRs, and genealogy to build a surname origins tree. That has moved on since, and I'm going to give you an update today. And there's also a video on how I built the Mutation History Tree, that's what I call it, for my GLEASON Lineage 2 group. And those are the GLEASONs from North Tipperary. So those are two videos that would be complementary to the talk that you're going to hear me give today. We also have documented this building process on my blog, the GLEASON DNA Project. And there's a variety of different blog posts over the course of the last 2 years, since the last time I spoke here at Family Tree DNA, that just explain the actual process in a lot more depth. So if you're somebody that likes a written explanation of what actually went on, then this is all documented on the GLEASON DNA Project blog. And I suppose one of the main reasons why this is now possible is because there's been a huge growth in the uptake of the Big Y test. And this is what happened with GLEASON Lineage 2 in January 2015. There were 2 people with a Big Y test, these 2 people here. But then in April 2015, it had increased to 3 GLEASONs. And then in June 2015, we had 5, including an NPE, whose great-grandfather was a GLEASON. And then by October 2015, we actually had 6 people who had done Big Y test within our group. And you can see the way that the tree is beginning to break up into various branches. That there's a big SNP block here which kind of oversees all of the GLEASONs, and then there's a branch here that splits into 2 branches, And this branching structure of the tree is becoming more evident as more people test. And then in June 2016, we had 2, 4, 6, and 3 is 9 people had done the big Y test, and the tree had become just that little bit more complex. So the more people that tested, the bigger the tree became. And then in August 2016, we still have the 9 people. We now have we have 10 big Y people tested in GLEASON lineage 2. And we've also been able to date each of those branches. And dating is not an easy thing to do, but we will be talking about it later on. And you can see that the TMRCA, time to most recent common ancestor, is about 1900 for these 2 people here who are brothers, 1650 for this branch here, 1350 for this branch, 1500 for this branch, and maybe going back to 1050, 1125, and 500 AD. So we'll talk a little bit about dating and the kind of problems that you have trying to assess that. The other big advance in terms of GLEASON lineage 2 is that having done 10 big Y tests on this group of what is now 37 people, I then identified all of those SNP markers that were shared by the GLEASON lineage 2 group, and also for each of those 10 big Y tests, I harvested the unique SNPs for each of those members, submitted them to Family Tree DNA, and they were kind enough to put them on the Z255 panel, which immediately became a very lineage 2 specific SNP pack. And I tested another 10 people in the project with this very specific SNP pack. So altogether, I've tested 20 out of the 37 members of the project with downstream SNPs. SNPs that are way, way, way downstream and more approaching the present day. So those are the 2 big things that have happened over the last 2 years. 10 big Y tests, and then the SNP pack, which is very lineage 2 specific. In December 2015, this is what the lineage 2 mutation history tree looks like. It wasn't a very pleasant one to look at, so it was tidied up. By a year later, we had 6 branches, 9 big Y tests, 29 members with 20 people on the tree, and you can see here the various SNPs on the left-hand side of the lines, and the STR markers on the right-hand side. And we had 6 branches, A, B, C, D, E, and F. 4 of those branches were defined by SNP markers, by big Y data. 2 of them were defined on the basis of unique STR patterns within the STR data. We'll take a little bit of a look at that. Those 2 branches, and you'll see them here because they're not highlighted in any color, were branch F. This was on the basis of an STR pattern, and branch E was on the basis of an STR pattern. Both of those branches were subsequently confirmed by the Z255 SNP pack testing, which showed that they did actually have a unique SNP marker that defined that particular branch. And then in November 17, up to the present day, we have 11 branches, 10 big Y tests, 10 SNP packs, 37 members. 32 of those members have been, we have been able to place them on the tree. So I haven't been able to place everybody on the tree, but I have been able to place the majority of my project members on this mutation history tree. So you cannot see the detail there, I'll show it to you later on. But what we're going to do today is look at the evolution of the tree over time, building a mutation history tree using the visualization method that I employed, which really is just kind of it's very much a hands-on approach. The other thing is, and to do this visualization method and build the tree, the first step is to identify the subgroups within the overall genetic group. Secondly, to then place each of those subgroups on a particular branch of the tree. Thirdly, check your data against the SAPP program, and I'll tell you about that in a moment. And fourthly, date the branching points. So those are the kind of 4 steps that I do in this visualization method. And we've mentioned the SAPP program. This is the SAPP program created by Dave Vance. And it's a wonderful program because 2 years ago, I had a wish list. And I said, I made some predictions. I said, in 5 years' time, in your GAP project pages, there will be a button, and you hit that button, and the mutation history tree for your groups is automatically generated. The good news is we're almost there. And Dave Vance has actually put together that program that allows you to do this. So we'll take a look at some of his outputs for this program later on. He also gave a talk just a couple of weeks ago in Dublin at the Genetic Genealogy Ireland conference. It's available on Facebook. It will be uploaded to the Genetic Genealogy Ireland YouTube channel within the next couple of weeks when I get home. But it's a very, very good talk explaining how the SAPP program works. So for those of you who like to do things the easy way, which is automated, you can just use the SAPP program and it will produce a mutation history tree for any of the major groups in your surname project. So a wonderful invention by Dave. But why would we do this? Why would you create a mutation history tree for a particular genetic group in your surname project? Well, there's a variety of different reasons. I think there are many benefits to both the project and to your project members. It's a very nice visual summary of a large amount of project data. And it's a nice way of just saying to people, look at this diagram. And I go, oh wow, okay, now I understand where I fit into the big picture. So it's a wonderful way of visualizing what you are doing for your project members. It also helps communication with project members because you can say, oh, you sit on branch F, and that means you're very closely related to people, and it looks like your common ancestor is about 7 generations ago. Now go away and see if you can find the data to actually document that and prove it. It allows members to see how they are all related to all other members. So it gives them a much greater sense of where they fit in the big family for that particular surname project group. It also gives a clear view of how the surname has evolved over time. And that can be very interesting, especially if you have surname variants in your project. And you can see when it happened and when they occurred. It also defines the branching points over time, and you can date those branching points, of course, as well. It shows how close or distant the various branches are to each other. And it probably gives you a better estimate of the time to most recent common ancestor of the branches than the tip tool that we would normally use to look at how closely two people are related to each other. So it gives you a better idea of the TMRCA estimate for branching points. It probably gives you a better date for the most recent common ancestor for the entire group. Now that might be the surname originator, or it might be within 100 or 200 years of the surname originator. And is a very useful visualization to add to your project publicity. And that will draw in more recruits and get more people interested in the work that you're doing because you've produced a very nice, pretty family tree for the entire genetic group. So, turning to the visualization method itself, first of all, the first step is to identify the subgroups. And to do that, you look at the results spreadsheet on either family tree DNA. My preference actually is World FamiliesNet. The reason being, it has these pretty colors. And the pretty colors are actually very, very important because the pretty colors help define the unique STR pattern for GLEASON lineage 2. So you can see that there's a nice blue line that virtually goes down the entire length. Another one here, another blue line here, a orange line here, another orange line going up there, blue line, and then I tend to ignore CDYA and CDYB because they're so fast mutating, it doesn't really make any sense. And then you've got a nice orange line here. Now, this is, of course, compared to haplogroup R1b1 modal. The modal signature for R1b1, that's just what Terry uses. But you can use modal haplotypes for further downstream subclades. In my case, that 255 would be appropriate. And I have used it in my results spreadsheet on Excel. Because what I then did is I took all of these results and I copied them over into an Excel file. And I'll show you that in a moment. But what you do with this results spreadsheet then is you group the unique STR pattern for the group is fairly obvious. And these are these lines that are virtually, that extend down the virtual length of the entire project. And this type of pattern would be relatively unique to GLEASONs of lineage 2. In GLEASONs of lineage 1, completely different color pattern. GLEASONs of lineage 3, completely different color pattern. So each genetic group within your project will have a unique STR pattern that helps to define that that person should belong in the group. And it's very, very useful. And what Terry Barton has done with worldfamilies.net has proved very, very useful for this type of research. So that's the unique STR pattern. Like I say, I downloaded all of this to Excel, and then to identify the subgroups, first of all, you group those people that you know to be related to each other. So 2 second cousins, or in this mass of STR results, you group them together. And in the Excel spreadsheet, it means highlighting the row of the second cousin, cutting it out, and pasting it up on the row below his known relative. And that way, from a group of 37, you're gradually moving people into subgroups within the overall group. So that's the first thing you do, is you group known relatives together, because their DNA signature is going to be virtually the same. There might be one mutation, possibly it's an exact match. But that's the first step. The second step, some people will have tested downstream SNP markers. They'll have done the big Y, they'll have done a SNP hack. Those that have sufficiently downstream SNP markers, you can group those people together. And I'll show you what that looks like in the Excel version of the spreadsheet in the next slide. The third thing you do to identify subgroups is that those people that are really, really tightly related to each other by virtue of genetic distance, you can put them together. And I mean a genetic distance of 0 out of 37, 1 out of 37. Those ones you can say, well, they're probably really tightly related to each other. Let me put them in the same subgroup as well. And the fourth criterion for subgrouping is to look at unique STR pattern for subgroups within the data. And when you look at this particular spreadsheet, and I've made it easy for you because on the worldfamilies.net format, we actually have lumped people together into their subgroups. You can see some unique STR patterns emerging for subgroups. So for example, this particular group here, everybody has a value of 10 for this STR, a value of 9 for this, a value of 9 for this, and a value of 17 for that. So it's a very unique pattern within the overall collection of STR markers. Let's look at another one. Here's one here. These 3 people are 17, 17, 17, and then we have 3 14s and 3 17s. So they could be another subgroup within the overall group. Here we have a 15, 2 15s on that side, 2 19s on that side. We have a group of 15s here, and 15 is relatively rare in this line. You see nobody else apart from this person here is 15, but he probably has different markers to the others. Yeah, he's got a 14 there. That could just be an individual mutation, but you know, that's the way you would you try and group people together that have the same STR pattern. Now, an STR pattern based on 1 marker is not as convincing as an STR pattern based on 3 or 4, like you see in the other examples. But it's still something that you put in the back of your head and think, could these possible people all be related because they have the same marker value and nobody else, or maybe only 1 or 2 people, have that marker value in the entire group. There's also a group of people up there with 14 for that particular marker. So those are the unique STR patterns for subgroups within the overall group. And you can see these patterns emerging as you analyze the data and as you look and become bog-eyed looking at this mass of numbers. But like I say, I transferred everything to a spreadsheet, and the members in yellow were related. These were 3 brothers. These were 2 second cousins. These 2 people were related as well. So that was the first criterion, known relatives. SNP markers, 2 of the brothers had tested, and they were positive for the same SNP marker. 3 people down here were positive for the same SNP marker. they were lumped together, and these are downstream SNPs as a result of the big Y test. These two people had also tested for this particular downstream SNP marker. These SNP markers were actually very similar to each other, very close by, so they were lumped together as well. The last two branches, branch E and branch F, it was based on the STR signature, a unique STR pattern in these two particular subgroups here. And that was later confirmed by SNP testing. So that is a summary of how you actually go about finding subgroups within a genetic group within your family, within your project. So the next step, once you've identified these subgroups, and of course you won't be able to put everybody in the project into a subgroup, which is why I haven't been able to put everybody on the tree. There's 37 members in the project. 5 of them I could not place on the tree, so they're put to the side. I'm still waiting to have enough evidence to put them into a specific group. But once you have identified subgroups, the next step is to place them on the tree. There will be several subgroups. You don't know how they are related to each other. You know, which comes first, where, you know, are some of them more closely related to each other, which are the most distantly related? You don't know. You need an anchor to start the whole process of placing them on the haplotree, on the tree of mankind. And in order to, and they also need to be placed correctly relative to each other. So this is where the tree building comes into place. You've identified the branches, now you have to place them on the tree. And in order to do that, you need an anchor. And the best anchor to have at the very, very top of your tree is the modal haplotype of the nearest major subclade. And for GLEASON lineage 2, it was Z255. And I extracted that Z255 modal haplotype from the OR-L21 haplogroup project. And again, it emphasizes the importance of having your members joining haplogroup projects so that they can generate these type of modal haplotypes that will then be useful for your particular surname project. So I use the Z255 modal haplotype as my anchor. Now that is about 2,000 years old. Z255 about 2,000 years old. And of course, with my GLEASONs, I'm only really interested in the last 1,000 years. So there will be 1,000 years of difference between Z255 and the most recent common ancestor for the GLEASONs of lineage 2. But I'm using Z255 as my anchor for now. And of course, when you build this tree, what in effect you're getting is the best fit, given the data that you have. It probably is a very good approximation of reality, but it's not reality. It's the closest you're going to be able to get with the data you have available. Having the Z25 modal haplotype as the anchor, you then identify single mutations within your overall results spreadsheet, because those single mutations that are not shared by anybody else in the project are probably specific to that individual, and you can kind of put them to one side. They will help when you're looking at the branching within a subgroup. So the subgroup might have 4 or 5 people in it, and those single mutations will help you place people on different branches in that subgroup. So it helps defining the branching structure within subgroups, but then you inspect each subgroup marker by marker, asking the questions, does this marker value differ from the marker value in the Z255 modal haplotype? And also, is it unique for that particular subgroup, or am I seeing a parallel mutation in another subgroup? And this is where you end up playing a game of chicken and egg. Which came first? And you're trying to see where the subgroups relate to each other, and what's the most parsimonious way of putting them into your tree. And by most parsimonious, I mean what configuration of mutations gives you the least number of steps for your mutation history tree. And I use the old technology of a paper and pencil, and I draw it out. Sometimes I need a little help from a relative. I use this relative. It can be a little bit mind-boggling, trying to figure out, does that come first? Or that, oh, if I put that one up there, then that makes more sense. That's less steps than what I had previously. It takes a while. It's easier than it looks. But once you've written it out on paper, then you can transfer it to Excel and make it look pretty. And that's how I generate my trees in Excel. The other thing that you can do is once you've worked it out for yourself using this visualization method, you can check it now against Dave Vance's SAPP program. And to do that, all you have to do is create a text file of your results. And you click on this button here, choose file, and that text file goes in, and it takes a couple of seconds, and it spews out a mutation history tree based on the data that you put in. But SAPP is much more than Fluxus. Now, how many people have used Fluxus? Okay, quite a few. It creates one of these kind of spider diagrams that you see down here, which is why I think this is what inspired IKEA to put together assembly instructions for their furniture, because that's what it looks like. So, and where is the ancestor there? Where does he sit? As a genealogist, when I saw this, I was like, I don't really understand this at all. I'm expecting an ancestor and descendants. And that's what Dave's SAPP program does. It actually produces a tree that looks like a genealogical tree. It allows you to put SNP data in, which is something that Fluxus does not do. So you can actually anchor various subgroups by putting in the SNP data. So you saw in the example that 4 of my branches, 4 of my subgroups, had SNP markers that defined them. Those can be put into the program, and you can anchor those subgroups with those SNP markers and say, these people are all descended from this SNP marker. These people are all descended from this SNP marker, and so on. The other thing that you can put into the program is actual ancestors. So if you have documentary evidence that several people are connected by the same ancestor, that ancestor can go in the program as well. It also produces a tree, and it also dates the branches. So this is another way that you can actually date the branching points within your mutation history tree. And this is the kind of output. You don't have to worry about the detail, but you get an idea of the actual structure. So Dave's program actually produces a family tree with an ancestor, with branches, with various branching points, with time to most recent common ancestor, or dating points for the branching here. So these are, in green you have the dates. It has all the STR markers that change or mutate over time. And you can see how it relates to my mutation history tree. Branch A is there, branch B, branch C, branch E is down there. Branch F is split between these 2 people here. Branch D is split between these 2 people here. This was an early version of the tree, and since then Dave has been constantly upgrading it and refining it. So the output will look slightly different now and much more akin to what I was able to achieve. But the important thing is that you can use this and double check your own visualization method tree against what Dave has produced. And using that, I was able to actually refine part of one of the branches in my tree. That was the old structure on the left. There was a little bit of a problem here because the date for the branching point here was 9, and the date for the upstream branching point was 5 to 7 generations ago. So that was wrong. And Dave's tree allowed me to see that there was a more parsimonious structure and a better fit for the data, and I was able to change my version as a result of that. So it's a great way of double-checking your visualization method. The last thing to do is to date the branching points of your tree. And there's 4 things that you can use to actually date the branching points in your tree. You can use pedigrees. So if you've got colonial American ancestry, and it goes back to the 1600s, and you've got several people tested, that is the best way of dating that branching point. That MRCA of all of those people you've tested from that colonial American line, that is the best way of actually dating the branching point for that particular subgroup. There's also the TIP tool, we'll look at that. There's the SAPP Programme, we'll look at that. And there's SNP data as well. So let's look at, so dating using pedigrees is the most accurate way of dating a branching point, but most pedigrees do not go back far enough. You know, and if you look at this diagram here, where are the 3 branching points? Those are the only 3 branching points that you could actually date using pedigrees. Everything else ends up with a single most distant known ancestor, and it's not connected to any other trees. And this would be very typical of Irish genealogical research and family trees. As far as the TIP report is concerned, what I do with the TIP report is I look for the midpoint value, that 50% mark. So the value that's closest to 50% in this case is 45.53%, and that is at the 8 generations level. So my best midpoint guess for the TMRCA for these particular people being compared is 8 generations ago. The most recent common ancestor was about 8 generations ago. But look at the range around it. And let's pick a 90% range. We want to be 90% positive, we've got the right range. Well, there's the 5% level, which is at 4 generations. There's the 95% level, or as close to it as possible, and that's 15 generations. So now we've got an estimate of 8 generations, but within a range of 4 to 15 generations. It's too wide. It's not exact enough. It's not genealogically relevant. But we can use the mutation history tree to triangulate on the various branching points. So for example, rather than just depending on comparing 2 people, if we compare, say, I put the number of generations back to each branching point here, underneath each branching point in turn. And you can see that comparing these 2 people here, you've got an estimate of midpoint estimate of 5 generations. Comparing this person here to this person and to this person gives you a midpoint estimate range of 7 to 9. One of the comparisons was 7, one of the other comparisons was 9 generations. Going back here, comparing and triangulating all these people onto this branching point here, you get a midpoint estimate of anywhere from 9 to 17 generations ago. And then the next branch up is 7 to 13. And the next branch up is 14 to 22. So you see that this is a very, very crude way of estimating and dating those branching points. Is there anything better? Well, we can use the SAPP Programme. And Dave's SAPP Programme, his TMRCA estimates are based on Ken Nordtvedt's interclade aging methodology, which I don't know a lot about at all. But it is a least squares analysis using STR differences and mutation rates. And you can see here that the nodes in Dave's SAPP Programme trees are written down here in green. The TMRCA is 8 generations within a range of 7 to 9, giving an approximate date of 1700 AD for the birth of that most recent common ancestor at that dating point, within a range of 1700 to 1750. Now that seems a lot more accurate, a lot more exact. I'm not going to say accurate, because everything I'm showing you here is accurate statistically and inexact genealogically. And that's a major important point, is that when we try to do this dating, it may be accurate statistically, but genealogically it's not exact enough. And it's like the story I tell of the genealogist who meets the statistician at the cocktail party, and the statistician says, "Oh, you'll be pleased by this. I started doing my family tree." And the genealogist is like, "Oh, that's fantastic. Who are you starting with?" "Oh, my grandfather." "Oh, really? When was he born?" "Ah, well, I'm 95% confident that there is a 90% probability that he was born sometime in the last 24 generations." Statistically exact, statistically accurate, but genealogically inexact. There is, yes, Dave's SAPP Programme also has SNP-based estimates. Now, SNPs are great for dating the more upstream branches of the tree, the reason being that you've got much more SNPs to play around with. But when you get down into a surname project, you may only have one SNP in each of the branches, and you're playing with a lot less data. And what happens when you play with less data? The range around your estimate gets very large indeed. But Dave has a SNP reference tree, and my Z255 group is here. You can see that Z255 is dated to 300 AD. The next one down is 550 AD. Then we have 1000 AD for A557. My particular branch is this one here, A5631. We have a date of 1150 for this, 1300, 1200, 1600. So he is using it to date, these various branching points. But at the end of all of these different methods for dating the branching points, you're still left with a big question. Which estimate is the best one? Thankfully, there is a very easy answer to this difficult question. And it is the one that best fits your preconceived ideas. So it's just like, you test with autosomal DNA, you get your ethnicity, makeup from a variety of different companies, and you're wondering which is the best one. Whichever one fits your preconceived ideas. That's the one you choose. Why? Because that's what we're geared to do as human beings. We will naturally be biased to what we want to believe. So, and I love this. This is from Donna Rutherford, who said this in Dublin. I said, I'm stealing that, and I'm using it. I'm letting you know in advance. So, whereas the pedigree method is the most accurate, none of us are going to have pedigrees that go back to every single branch in our mutation history tree, certainly not before 1600 in the majority of cases, and for many of us not before 1800, leaving 80% of the tree undated. But, and the other methods are statistically accurate, but not genealogically exact, and it's highly likely that they never will be. But we will always be prone to wanting to pick the one that best suits our preconceived ideas. Take-home message, dating is difficult, and it will just give you ballpark figures. And if you want to know, did my 7 times great-grandfather, was he born in 1570 or 1600, it probably will never tell you that, even if we go up to 500 STRs, because the range around the estimate is still going to be far too large. So that's how we ended up with this mutation history tree for GLEASON lineage 2, and I'm going to show it to you now in a little bit more detail, but having created this tree, the next thing that I did was I added on the pedigrees of each of the members like baubles on a Christmas tree. And that is what I'm going to show you now is the mutation history tree. Here it is here. It's available as a PDF file and anybody can download it. But I'll just show you what it looks like so you can get a better idea of what's involved. So there we have Z255, dated to about 300 AD, and we come down through the various mutations. You can see that related surnames, Tracy, Miller, Phelps, Prendergast, Carroll, McMahon, Webb, and McDonough, they branch off as time goes on, and there are STR mutations along the way, which I was able to get from Nigel McCarthy's brilliant work on the Z25 project. So a lot of my work was based on what Nigel has done. You can see that when we get down to A5631, this is the SNP, that is the overarching SNP for all the GLEASONs of lineage 2. And that is dated to approximately 30 to 32 generations ago. And 30 generations ago is going to bring you back to roughly 1000 AD. So are we looking here at the originator of the GLEASON surname in this particular genetic group? That's the fascinating question. And I think we're very, very close to him. One of the main reasons I think that is because, and I'll be talking about this tomorrow, when we look at branch F, this branch here was so distantly removed from everybody else in the project that it took us actually months to decide that this person was in fact belonging to the project, because we missed it. The genetic distance from branch F to other people in the project, the minimum genetic distance is, I think, 9 out of 37. 9 out of 37, 10 out of 37. The maximum genetic distance from anyone in group F to anybody in the rest of the project is 13 out of 37. And this is SNP confirmed. They are related to each other by a downstream SNP. Moving across the project, we have these various groups, and you can see that the colored lines indicate that the SNP in question, which in this case starts up here with BY5706, it comes down here, it comes over here. So this person down here, G05, is BY5706. This branch over here, BY5706, then has some additional SNPs below it, BY5707, 5708, and 5709. They go down as far as here, and then additional downstream SNPs occur in those more downstream branches. So it's a great way of visualizing where the SNPs occurred in the group. And then coming over here, we have a crude timeline on the side, and you can see it goes back to about 1050, which is where SNP dating is also predicting that overarching SNP for this lineage occurred. And it just gives you an idea of what was happening over the course of the 1,000 years. Then I have the various kit numbers that people tested, and then we actually have their ancestral lines. And you can see the majority of them go back to about 1800. You can see them all there, and that's all we know. They all end about 1800, and we don't have many of them that actually have a common ancestor. The MDKA profiles then is I encourage the members to document the details of their most distant known ancestor. What was his surname, his forename? So we have a Thomas and a Thomas coming from the same area and on the same branch. Is this a family name that was passed down to this particular branch of the GLEASONs? We also have where they were born, where they died, the spouse's name. Some of the families actually have a nickname. So for example, my family was known as the GLEASON Rabbits, or the GLEASON Macavadis. We're not entirely sure what nickname our family had. GLEASON Rabbit would have been called GLEASON Rabbit because rabbits would have been captured, killed, and sold as meat, and you get a shilling for each of the rabbits. And people around Chile remember the GLEASONs from my area cycling around with dead rabbits hanging off the handlebars. So that might be very much where we got our surname nickname. The reason why the various GLEASONs in that neighborhood had nicknames was because there were so many of them that you had to distinguish between the various GLEASON families in North Tipperary. There is a saying, if you throw a stone, you'll hit a GLEASON. It's an observation, not a recommendation. I need to emphasize that. So that is the mutation history tree for GLEASON lineage 2. And these are the key learning points. The nearest subclade modal haplotype is the anchor for your mutation history tree. The SNP markers fix the more upstream branches of the tree, say 500 to 1,000 years ago, and it's very important to get that anchoring in the upper branches of your tree, just so that you avoid any chance of convergence more downstream. 37 STR markers are sufficient for grouping, but not usually for subgrouping. Okay, so they'll get you into lineage 2, but they won't necessarily help identify a subgroup within lineage 2. And that's why 5 people still remain ungrouped within this particular lineage. They're also not optimal for placement on the mutation history tree, nor for dating of the branching points. So 67 or 111 marker data is much more preferable. The SAPP program is a very useful tool for double-checking your work. The dating of the branching points is never exact enough unless you've got pedigree data, genealogical data that actually dates that branching point. But this is an excellent overview of all of your data for a particular genetic group, and it helps focus further research. it will always be a best fit model. It will not be reality, but it is the closest thing you're going to be able to get to it. So that's it from me. If there's questions, then I'd love to take them. And then thank you again to Bennett, Max, Janine, the entire team. Thank you. So we might have a few questions. We have a question from John Farris. I don't know if we have a microphone, Janine. Do we have a microphone? No. You shout, John. I'll repeat it so everybody else can hear.
You had red boxes that were broken. Was there a significance to those broken red boxes?
There were red boxes. There were boxes that had a red broken line around them, and there was a significance to those. And it's a very astute question, and I can't remember why they were. I think it was because these were. I think they were previously en route. I think that's what it was. You know, I said there were 5 members that I couldn't group. Well, the SAPP program grouped them, but I think that it's dodgy grouping because I don't think there was enough data to accurately put them on the tree. And what the SAPP program is going to do, it's going to put them in the best fit position, which may or may not reflect reality. So that's why I kind of highlighted them as a kind of a question mark. I think that was the main reason why I did that, yes. Okay, oh, question here. How do you enter SNP data? Or the mechanics of using the SAPP, yeah. Right, well, I can actually show that to you. I think we have a little bit more time. What you do is you have a text file, TXT file. If I make that big, it's going to, there we go. And that's the TXT file there. If I click on, so you actually input it into the TXT file. There are instructions by clicking on the FAQ or the inputs on the SAPP website. It actually gives you instructions of what to do. And by simply choosing the file and then clicking on execute, within a couple of seconds, you'll see that it's analyzed the data for my GLEASON lineage 2. It's completed the tree successfully. There's a table of the STR data. So it has replicated exactly what you see on the Family Tree DNA website. Number 1. Number 2, there's the original genetic distances. So just like, I know Whit is here, Whitathi's tool for genetic distances, this is very, very similar to what we generate with Whitathi's tool. Not only does it give you the original genetic distance, but then having put people appropriately in the mutation history tree, it actually adjusts the genetic distance and gives you a much more accurate genetic distance based on the placement in the tree. And you can see there that a lot of people there's a genetic distance of 16. So 16 out of 37. So it's different from the original genetic distance because it's taking into account the placement of the people on the tree and the various STR values that intervene. This is where you put this is how your SNP data appears. You'll actually write it in the text file, and there's a simple way of doing it. And then this is how it appears. So I've got all of these SNPs in GLEASON lineage 2. These first 3 people here are positive for the first 4. These ones are positive for those ones. So that's how it appears in the table. And then it has some STR data here down as well. It's calculating the mutation rates for the STR markers based on your data in this specific genetic group. At the very end, it says get the SAPP tree. It's downloading it somewhere down here. Okay, and there it is there. So the SAPP tree comes up, and we can increase that, and you can see that that is the SAPP tree with the dating points. So it's a very simple program to use. The difficulty is the SAPP program publicly available? Absolutely. Just if you search for it or you go to jdvtools.com, you'll find it. Dave Vance, the SAPP program. How do you convert the CSV file to a text file? With great difficulty. It's very fiddly, but what I do is Dave has actually given us a sample file, and if I go back to his yeah, if you go into the inputs or the FAQ, you can download his sample file and just replace the data in the sample file with the data from your own particular genetic group. I do it manually and it's a pain in the neck. And I do it for every individual. Well, the thing is that you can copy and paste it from an Excel file into the TXT file, but that screws up the formatting somehow, and you just have to play around with it a huge amount. So it would be easier if you could get somebody else to do it. Through trial and error, you know, just drink lots of Captain Morgan, you'll be fine. Through trial and error, I was able to do it. So that's how you convert a CSV file to a text file, or how do you make the TXT? Yes, we covered that. How do you differentiate each individual SNP data when entering into SAPP? We covered that. Is there one record of SNPs per tester? Yes, well, it depends really how many people, the number of people that have done SNPs, you just put in their SNP data, and that anchors them. It won't anchor anybody else who hasn't done that particular SNP testing, but it will anchor those people within the tree.
Last question.
Your first mutation tree slide used a format of a block diagram. It is used in many online O1B subgroup projects. What software produces these diagrams? I have no idea. Alex Williamson's tree is where for the first one, I just kind of copied and took a screen grab of the SNP block from Alex Williamson's tree and just plonked it on that early version of the mutation history tree for GLEASON lineage 2. The two subsequent versions, of course, I've done in Excel. So all those pretty colors, everything you see there is just generated in Excel, and it's a relatively easy thing to do. So that is it, and thank you very much for your questions.
Thanks, Morris. We have a break now, then they're going to move the wall and we'll be back into one big section. So 15 minutes, please. Thank you very much.
Only, like we see that there's like say this the 2519 positive on their examples.
Does SAPP support the extended Y full